Sir, excuse me, sir.
Yeah, please.
So like during the yesterday's exam, so like what happened is that at the end of the time, the server got like very busy, sir. Because of that, my submission did not get submitted.
So
And
can
I
you
was,
mail me? Can you
yes,
mail it to me?
immediately I've mailed you, sir.
What is your name?
Hemant Rao, sir. Gandham
Yeah,
Hemant.
okay. So what we'll do, we are doing for such cases, we are doing a proxy submission. That means whatever you have mailed us, that version before the deadline, we are doing a proxy submission. Okay, so it will be evaluated.
Yes,
Sir?
Yeah.
Sir, I told you like in the class itself, sir, that I was not able to find the recording. So you told that for that MD5 hash, you'll give some extra time.
Oh, that you will give extra time. You don't worry. That
Yes,
will
sir. I submitted the text file within time, but I couldn't
yeah,
submit that.
wait. See, okay, you can do it later. Don't worry. You don't delete it in your computer. If required, we will ask for it. Right now, nothing need to be done. If we ask for it, you give it to us.
Okay, sir. Thank you, sir.
So like submission be not like, I mean, I have waited till 10 and immediately within 10 2 I have submitted, sir. Like you can understand, no, sir, because
we have extended it till 10:10.
So no, sir, like by 10 it was closed, sir. I was
again we opened it.
So like I was not aware of that, sir. That's why before 10:10 only I've sent you the mail.
Okay, fine, no problem. What is your name?
Hemant Rao, sir. Gandham Hemant Rao.
Oh yes, yeah, okay. Yeah, we'll do it. We'll do a proxy submission. But see, this time, one thing I should also mention, this time we are doing because it is first time. From the next time, you have to be careful. You have to try out beforehand, see that the login password is working. See, the password can be remembered. So you open a browser, you log in and stay logged in. Okay, so I mean, be a little sincere. You log in and see that everything is working. Okay, see, otherwise, no, this is next time we'll probably not do it. You have to be careful.
Okay, sir.
Okay, anyway, all right. So we defined what is a lattice. A lattice is a partial ordered set where wait a minute. Yeah, where every two elements have a meet and a join. So you pick up any two elements, they will have a meet as well as a join. Then such a partial ordered set would be called a lattice. So we have seen certain examples. So in order to, if you are given a Hasse diagram, for example, it can be in other form also, need not be an Hasse diagram. All you need to do is to see if every pair of element have a meet as well as a join. Okay, so definition of meet and join, you know, definition of meet is the greatest lower bound and the join is the least upper bound. Now, let us see, there are, so see, it is kind of, we define two operations. One operation is a meet operation. You can think of the meet as an operator which takes two elements and produces a third element. Similarly, join takes two elements and produces a third element. Maybe the third element is one among these two, but it's kind of an operator. Now we'll see some of the properties, some of the ordering properties that are satisfied by this meet and the join operator. I'd like to particularly want you to understand this concept of join and a meet, because you can see these are exactly the Boolean algebra operation, the usual logic operations that we'll do. We'll explain why you are coming to this long route to the logic operations. You'll soon understand, because this is a much more general structure. This is a much more general structure, but to a particular restrictive case, this will be the usual logic operations. Okay. Okay, so let us look at some ordering properties of these join and meet operators. Okay, so x join y, it's an element of the poset. It's an element of the poset. So that element is less than equal both x and y. Similarly, both x and y are less than equal the join of x and y. I think this is obvious. You take, for example, this is x, this is x. I hope you can see the pointer. This is x and this is y, let's say. So the join of x and y would be, in this case, x itself. It can be something else. For example, if you take x and z, their join is u, and u is less than equal to both y and z. U is less than equal to both y and z. All right, and this also is, I think, obvious that both x and y are less than equal to the join of x and y. Sorry, this would be meet of x and join of x and y. Both x and y would be less than equal to the join of x and y. Okay, so that is by definition, because the meet of x and y is nothing but it is the greatest lower bound. So x and y has to be greater than this by the definition of the lower bound. Okay, so can you tell why the second statement is true? That means if x will be less than equal to y, if and only if the meet of x and y is x itself. Let's take an example. Say this is x and y. This is x and y. Let us prove if and only both direction. So if x is less than y, if x is related to y, if x is less than equal to y, then definitely the meet of x and y will be x. Now let us look at the other way around. So if the meet of x and y is x, y is less than equal to y. Can you tell why meet of x and y is x? So let's say these are x and y, and their meet is x itself. Then why is x less than equal to y?
Sir, if meet is equal to x, that means x is the maximum element of the set of all z,
right,
such that z is less than equal to y, and z is less than equal to x. Since z is less than equal to y and x is an element of that set, x is less than equal to y.
Very good, very good, excellent. That's the proof. Okay, so similarly, the other way around, you can prove that suppose these are x and y. If the join of x and y is y itself, the join of x and y is y itself, then x is less than equal to y. You can have a similar proof. If the join of x and y is y itself, these are x and y, then x must be less than equal to y. All right. Okay. Now let us look at the third theorem, which is something we'll use in proving other theorems. Besides this obvious things, we'll use these things for the use of other theorem. That is, if x is less than y, if x is less than equal to y, then the meet of x and z is less than equal to the meet of y and z. So it's kind of, you can, if x is less than y, and if you consider the meet of x with another element z, and the meet of y with another element z, then this meets, or the meet of x with the z will be less than equal to the meet of y with z. And the other way around. I mean, other way around means this also. So if the join of x and z, if x is less than equal to y, the join of x and z will also be less than equal to the join of y and z. So these two rules, they are sometimes called the complemented theorem. Not complemented. Okay, what is the name we have for them? So the thing is that there is, I mean, most of the time it is the case, not always. So you are basically replacing the join by a meet, and the similar theorem holds. We'll see that many cases does correspond, that type of corresponding theorems exist. Okay, let us try to prove this, that if x is less than equal to y, then x meet z is less than equal to y meet z. Okay, so let's define two additional elements, u and v, such that v is the meet of x and z. So v is the meet of x and z. This is v, this is the meet of x and z. And u is the meet of y and z. So u is the meet of y and z. Okay. So you know, if v is the meet of x and z, so v is a lower bound for both. V is a lower bound. Why is this second statement true? V is a lower bound for both y and z. Can you tell why v is a lower bound for both y and z? Anybody? I need to apply two rules. First of all, I need to apply this definition of meet. I need to apply this definition of meet. And secondly, you remember one property of the partial order relation. If
So
x is less,
transitivity.
transitivity, exactly, transitivity. So, okay, so why v is a lower bound for y and z? Why v is less than equal to y and less than equal to z?
Sir, v is less than equal to z because v is the meet of those, and
Very good.
v
And
is
why?
less than equal to x as v is meet of x and z, and as x is less than equal to y, v
Very
is less than equal to y.
excellent. So v is a lower bound for both y and z. Okay, but u we have defined to be the meet of y and z. U we have all defined to be the meet of y and z. So naturally, u is the maximum among all lower bounds of y and z. V is a lower bound of y and z, and u is the maximum lower bound of y and z. Okay, so naturally v should be less than equal to u by the definition of the maximum lower bound. By the definition of the maximum lower bound, v should be less than equal to u. V should be less than equal to u. And as we have defined, so which means x meet z is less than equal to y meet z. Is that clear? So v is a member of the lower bound of v is a member of the lower bound of y and z, and u is the another member of the lower bound of y and z, but it is the maximum member of the lower bound of y and z. So naturally v should be less than equal to u. Okay, so this I have proved. So how can you prove the corresponding theorem for join, that x join z is less than equal to y join z? How do you go about the proof? How do you go about the proof? Can anybody tell? Simple. I think in 3 steps you can prove it. Similarly, you have to assume two elements v and u, where v is the join of x and z, and u is the join of y and z. Okay, then what will be the argument? I am trying to prove this second part. I'm trying to prove the second part. Yes. So anybody?
Sir, by transitivity, u is an upper bound for x and z.
Right. Very good. And then what about v?
V is the maximum. V is the minimum upper bound for u for x and z.
Least
and
upper
u
bound. V is the
and,
LUB of x and z. Then
and u is some upper bound, so v must be
right.
less than
Very
equal
good.
to u.
Very good. Very good. So exactly the same type of argument. Okay. So now using these first 4 properties, can you prove the 5th property, that it's a transitivity property? That means if x less than equal to y and z less than equal to w, then x meet z is less than equal to y meet w. And similarly, x join z is less than equal to y join w. So how can I prove this? The 5th one. Or you can make a construction, you can give any other proof also. So how do you prove it?
Sir, X meet Z is less than equal to Y meet Z, which is
Very good.
equal to Z meet Y, which is less than equal to Z W meet Y, which is equal to Y meet W.
Exactly. Yeah, so that also can be easily proved. Okay, so these are the, but okay, when you, now that we have got the proof, you try to kind of remember these properties. Remember these, they are very easy to remember. First one is okay, that's the definition. Second two are kind of, you can imagine X and Y are directly connected by an edge. Okay, directly connected by a chain. So the higher one has to be the meet and the lower one has to be the join. So X is less than equal to Y in Hasse diagram. I'm talking about Hasse diagrams. And the fourth one is kind of, if X is less than equal to Y, if you take a third element Z and take the meet with X, it will be, and take the meet with Y, this meet will be less than the meet with Y. So that's it. And the fifth one is kind of a transitivity. Fifth one is kind of, not transitivity. I should not say it is transitivity. Okay, so it's kind of, you can, if you have X less than Y and Z less than W, less than equal to W, you can sort of combine them. You can combine them. Okay, so these forms you try to remember. Okay, so let us go into some more properties involving. So you gradually see that, okay, these meet and join are operators. Now we are considering expressions using this operator and the parenthesis. We are trying to kind of talking about larger expressions involving some join between some elements and then meet between some elements. We are constructing larger expressions. I think you already can guess the motivation, because in our logic circuits, this will correspond to logic operation, so will be larger circuits. These are nothing but larger circuits. Okay, so these are the usual properties of the meet and join operator. Commutativity. So the meet of X and Y is same as the meet of Y and X. How can you prove this? I think this follows from the definition. Similarly, the join of X and Y is same as the join of Y and X. How do you prove associativity? That means if you first take the meet of X and Y and then take the resultant elements meet with Z, it's same as the first you take the meet of Y and Z and take the resultants meet with X. How do you prove the associativity? The usual associativity rule. So basically, this statement, this law or rule would read as, or theorem would read as, meet is associative and join is also associative. Join operator is an associative operator. Meet operator is also an associative operator. So how do you prove that?
Here, like, is it necessary to mention that the meet should exist?
Yes, of course, but it is a lattice.
Okay, lattice.
It is a lattice, so any two elements will have a meet.
Okay, sir.
So okay, maybe I missed it. So all these properties we are talking about will hold only on lattices. So all these properties we are talking about will hold only on lattices. It will not hold on lattices precisely because the point you said, that there may not be a meet or a join. So then it's meaningless to talk about it. That's exactly the point. Very good. Okay, so how do you prove associativity? So how do you prove associativity is that, so you apply the definition of meet. X meet Y is less than equal to both X and Y. Okay, so X meet Y will be less than equal to X, and by the other property, if you this fourth property that we have here, this fourth property that we have proved, using that we can show that if you meet this result with Z, wait, no, sorry. So you look at this, X meet Y meet Z. So this X meet Y meet Z, should be less than equal to both these x meet y and as well as z. So that's what I've written. So this is the definition of x meet y is less. So x meet y is less than equal to x. And okay, now how do you apply the transitivity? Can you tell why is? Wait a minute, am I making a mistake? Okay, yeah, okay, fine. Fine. So let us go one by one. Yeah. So why is these two lines true in the proof? I am trying to prove the associativity of meet. Why is the first line true? First point true? Anybody?
Property 1.
Property 1 is the definition of meet. Okay, and what have I got there? I have applied it twice. So x meet y meet z will be less than equal to x meet y. And again, x meet y will be less than equal to x. Again by the property. Okay, so we have already shown that x meet y meet z is less than equal to x. Okay, now let us look at the other part. So similarly, x meet y will be less than equal to y. X meet y will be less than equal to y. Okay, so now let us combine these two. Let us combine these two. Okay, so I think the third point is obvious. Can you tell how do I get the fourth point? Can you tell why do you get the fourth point? Fourth bullet point.
Sir, by the previous theorem we proved.
By this theorem? This theorem?
Yes, sir.
Okay, so how do you apply that theorem?
Sir,
This is the direct application of that theorem. Is the direct
yes,
application. Sir. So because we have already proved that x meet y is less than equal to y. So now I apply that theorem and say that x meet y meet z is less than equal to y meet z. By applying this theorem. So that these two statements are following from that theorem. Okay. So let us see. We already have that x meet y meet z is a lower bound on x, and x meet y and z is a lower bound of y meet z. So look at point 3 and point 4. Look at point 3 and point 4. Okay. So the left hand side is same, x meet y meet z, that is less than equal to x. Then we have x meet y meet z also less than equal to y meet z. Okay, so x meet y meet z is a lower bound for both x and y meet z. Okay, so so that's the definition. It's a part of lower bound of both. So and it's a part of lower bound of both. And what is this definition? X meet y meet z. It is the greatest lower bound of x and y and z. So I think this is obvious. So x meet y, this line is a lower bound on both x and y meet z. And this one, the right hand side of the last equation, statement, that's the greatest lower bound of x and y meet z. That's the greatest lower bound. So obviously the lower bound will be less than equal to the greatest lower bound. The first line is the lower bound and the second line is the greatest lower bound. So naturally this one will be less than equal to the greatest lower bound. That's proved. Is it okay? Is it okay, or there is some confusion? It's actually pretty easy for all of you. Okay. So, okay. All right. Okay. So now let us go to look at the third theorem. Third theorem. This is very important.
Sir, we didn't prove they're equal.
Okay. So very good. So you can now proceed the other way around. You can now proceed the other way around. So you start with y meet z meet x, and then you will be able to show that y meet z meet x will be less than equal to
Yes,
x
I
meet
got
y
it.
meet z,
Yes, yes.
and by antisymmetry this will be equal. Okay. All right. All right. So we have associativity. Now let us look at this important property. It's called the absorption property. So you consider x join y. You consider x join y and take the meet of that with x, and you get back x itself. You get back x itself. Okay. Similarly, you take the meet of x and y and join that with x, you get back x itself. Get back x itself. We'll prove that, but first let me talk about this. So this is a very important property. In fact, all the logic minimization, the Carnot map and everything we talk about are true, are correct, because this absorption property holds. The entire Carnot map is based on this absorption property, with this meet and join being the and or operators. Okay, so let's idempotence is easy. So x meet x is x itself. By definition, it follows. Similarly, x join x is x itself. By definition, it follows. So let us prove the associativity we have proved. Let us prove the absorption. Let us prove the absorption. Okay, so what does absorption says? You take the meet of x with the join of x and y, you get back x. All right, so by the definition of join, x is a lower bound of x is a lower bound of x join y. The definition of join. So x, so the meet of, so you see this x is less than equal to x join y. X is less than equal to x join y. So you take that meet. So you now apply this rule. You apply this rule. X is less than equal to y if and only if x meet y is equal to x. The second point. Look at the second point. Now we'll apply that. Okay, so we have already proved that x is less than equal to x join y. So what will happen if we take the meet of the left hand side of this inequality with the right hand side? What will happen? Which one will get? Which one will get? X is less than equal to x join y. So if we join this left hand side of this first inequality with the right hand side, if you meet the left hand side with the right hand side, that's what we are doing here. Which one will get? The left hand side or the right hand side? So understood what I am getting? What I am saying is this. So if x is less than y, then x meet y is x itself. So if x is less than y, x meet y is x itself, the lower one. That's what I am applying. X is less than equal to x join y. So if we meet x with x join y, which one will you get? You will get x join y or x? You will get back the lower one. The lower one in this case is x. Lower one I am referring to Hasse diagrams. Okay, so the lower one is x, so you will get back x. Okay, so absorption is easy. In fact, you can get back idempotence by applying absorption twice. You apply absorption twice, you will get idempotence. Okay, so there is a principle of duality. Maybe you can see from these theorems is that if you take a theorem and replace the meets by the joins, you interchange the meets and the joins, that is still a theorem. That is still another theorem. Okay, so that's the principle of duality. That's the principle of duality. Okay, so okay, let us go ahead. You just try to remember these properties. These are the usual algebraic properties. You have a commutativity. It is commutative, so it doesn't matter which order you take the meet operation. There is a associativity. There is a absorption, and there is an idempotence. Can you tell any other algebraic property we have not written down, which is important, we use in usual algebra, which we have not written down here? Can you name any other property? Anybody? Is there some other property?
Of identity.
Distributed property. What does the distributed property say? Say, for example, if you have x meet y, join z, what would the distributed property say? Or x join y meet
x meet z, meet of y meet z.
Exactly. So we say that meet distributes join and join distributes meet. Meet distributes join and join, but that we have not yet proved. That we have not yet proved. That's in fact, that's not always true. That's not always true. So other four usual algebraic properties we have proved for lattices. They hold in any lattice. You take any lattice and you define the meet and join operators. These four theorems will hold. These four properties will hold, always hold. Okay, I have not yet talked about the distributed. Distributed may hold, may not hold. Okay, let us look at some other properties of a lattice. Some other special properties of a lattice. Okay, so a lattice would be called a bounded lattice if there is a maximum element, one single maximum element, let's call it 1, and one single minimum element, maximum and minimum are unique, one single minimum element, let's call it 0. And the following identities, because they are maximum and minimum, the following identities will hold. The following identities will hold. So if you take the join of any element x with the minimum element 0, you get x. Okay, you take the join because of commutativity, either thing is allowed. You take the join of any element with the minimum element, you get x. With the minimum element, you get x. Similarly, you take the meet of any element with the maximum element 1, you get x again. You take the meet with the maximum element, you get x again. And you take the meet with the minimum element, you get the minimum element. You take the join with the maximum element, you get the maximum element. You get the maximum element. Okay. So I think this is kind of consistent with our usual AND and OR gates, AND and OR logic. It's kind of consistent with that. So a bounded lattice is one in which there is a maximum element as well as a minimum element. Achha, can you prove that why every finite lattice will be bounded? Why every finite lattice will be bounded? Because kind of you see that we said that any two, if it is to be a lattice, then any two element will have a meet and have a join. Okay, we'll have a unique meet and we'll have a unique join. Okay, so if you take the entire lattice, and you will have a maximum element. You will always have a maximum element, and similarly, you will always have a minimum element.
Excuse me, sir.
Yeah, yeah.
So what is the difference between finite lattice and infinite lattice?
Yeah, so it's the cardinality of the poset. Cardinality, not the poset, cardinality of the underlying set. It's just the cardinality of the underlying set. So can you give an example of an infinite lattice? Finite lattice we have seen a lot. Can anybody give an example of an infinite set along with a partial order relation, which is a lattice? Can anybody give an example of an infinite lattice?
Integers with less than equal to.
Integers with less than equal to. How do you prove that it is a lattice? That is, any two integers will have a meet and a join.
The meet is the lower integer and the join is the upper integer.
Okay, so it's a valid lattice, because if you pick up any two integers, the max of these two is the join, and the mean of these two is the meet. Okay, so it's a valid lattice.
Sir.
Okay. Huh.
So for natural numbers, the same inequality, should we tell it as a partially bounded lattice, or will not tell it as a bounded lattice?
Yeah, so now the next question, is it a bounded lattice? That means, can you find a maximum, one single maximum, so that you take the meet of that, with, you take the join of that with any integer, you will get back that integer. Does there exist such a single maximum?
No, sir.
There cannot be maximum. Similarly, can there be a minimum?
Yes, sir.
That is a minimum, but maximum is not there. Similarly, if you take negative integers, if you take all the negative integers also, from 0 to say minus all the negative integers, then do you have a minimum? And the usual less than equal to relation is the, you don't have a minimum. So these are two infinite lattices which are not bounded. They do not have a maximum and minimum element. Any other finite lattice, we can always find a maximum and a minimum. You can always find a maximum and a minimum. Okay, why can you, for a let's look at the set of all positive integers. So why is not there a maximum? Why is not there a maximum? So what is a maximum? What is the maximum of a lattice?
Which is greater, means it is the greatest element of that set.
Right, it is the great. So you take any element in the lattice. If you take any element in the lattice, it should be less than equal to the maximum element. Okay, so for the set of integers, there is no such maximum element. There's no such maximum element. Okay, you can always add one and make it more than that. You can always add one and make it more than that. Okay, so but the finite case, it kind of directly follows from the definition that there will be one maximum and one minimum. One thing I'd like you to remember is that from now onwards, the maximum for ease of communication will denote the maximum by, we'll call it 1, and the minimum we'll call 0. Okay, maximum we'll call 1, minimum we'll call 0. Okay, so now with this, okay, so this is the definition of bounded lattice. Now let us come to distributed lattice. So that means it is a lattice where the distributive properties also hold. Distributed properties also hold, which means that if you take any three elements x, y, and z from A, if you take any three elements x, y, z from A, then these distributions hold. These distributions hold. That means the meet of x with the join of y and z is nothing. You first take the meet of x and y, then take the meet of x and z and join these two, and they will be the same. They will be the same. Let us see. Let us look at the first lattice. Let us look at the first lattice. Okay, see, in all these three lattices that I have drawn, you see these are finite lattices. There is a maximum and a minimum. So this is the maximum in each case. The top one is the maximum in each case. We are calling it 1, and the minimum is 0 in all 3 cases. Okay, now let's see if distributive property holds. Note that you have to show that this distributive property holds for all xyz in A, any xyz in A. Okay, so let us see for the first thing, first Hasse diagram. So ABC are 3 elements. So does distributive property hold? Does distributive property hold? So rather, my question, let me pose the question this way. So if this property, distributive property holds for all x, y, and z, I would call the lattice to be a distributive lattice. I'll call the lattice to be a distributive lattice. So my question is, are these 3 lattices distributive? Which of these 3 lattices are distributive? So the first one, is it distributive? Let me see if all 3 are coming together. The first lattice, is it distributive? The first lattice, is it distributive?
No, sir.
No, sir.
Yeah, because you can see there are these 3 elements A, B, C, where the distributive property, you cannot equate these 2. You cannot equate these 2. The second one, is it distributive? It's also not distributive. Okay, it's also not distributive. Okay, because you see the meet of A with the join of B and C is A itself, meet of A. What is the join of B and C? Join of B and C is what is the join of B and C?
1.
What is the 1? And what is the meet of A with 1? What is the meet of A with 1? A is the lower one. Similarly, let us look at this. What is the meet of A and B?
B.
B. What is the meet of A and C?
0.
0. And so B, what is the join of B and 0?
B.
B. Okay, so distributive doesn't hold in this case. Distributive property doesn't hold because you are getting different level. So if distributive property held, then this first line would be same as the second line. This would be same as this. So this is not distributive. What about this one? What about this one? The third Hasse diagram. So what is B join C? What is B join C?
1, sir.
B join C is 1. And what is A meet 1?
A.
A. What is A meet B? A meet B? B. And what is A meet C?
0.
0. So what is B join 0? B.
B.
So again, this is not distributed. Achha, can you mention, can I include an additional relation or rather additional edge in this Hasse diagram, additional member of the relation, so that it becomes distributed? What is the additional thing we should draw to make it distributive? Any of this? Can I have something to make it distributive? Can you suggest something? Can it be by a minimum modification? Can you make it distributed? Or do you need more elements?
Sir, if we join E and C, maybe.
Very good. Okay, so what happens if we join E and C? If we join E and C, then what is A meet B join C? What is B join
It will
C?
be E, sir.
It will be E. Very good.
Sir,
So what do you mean by joining E and C?
Yes, sir.
I include an additional relation, additional member of the relation that E is less than equal to C.
Yes, sir, but sir, which direction is it, sir?
Oh, that you tell which direction. Should C be
Sir,
less than?
E should be greater than C.
E should be greater
E
than
is
C.
less
So
than.
you should.
Okay, sir. Yes, sir.
you move E higher and establish a relation between E and C. Then what happens? Does it hold? What is B meet C then? B meet C is still 0 and B join C is still 0. No, B join C is
Sir, it would be yes, sir. It is matching.
E, it will be, it is matching. Okay, so if you have C less than equal to E, additional H in this Hessian diagram, then it will become a distributive lattice. Okay. All right. So this is one exercise. Let me give you.
Also,
So-
I think still it won't be distributed.
It won't. So can you find an example? See the establishing
D, E,
distributivity.
and C.
Exactly. So establishing distributivity property is little involved because you have to show this for all X, Y, Z in A. For all X, Y, Z in A, you have to show. You can always find a counter example where this doesn't hold. Anyway, I mean, let us go ahead. Maybe this is, in fact, we'll see later, distributive lattices have a very nice structure. If you look at their Hessian diagram, they have a very nice symmetric structure. Okay, I'm coming to that. They have beautiful symmetric structures. And that's why they are so good as Boolean algebra structures. Okay, so one small exercise I'll not ask you to do now is that if you take the power set of any set, and the set inclusion is the relation. So so you can naturally see if set inclusion is the relation, then the usual set intersection and set union will be the meet and join operation. This you can, okay, this is also a good exercise. You take the set inclusion as the less than equal to operation, and then you can see if you consider a power set of any given element, a given set, say A, then the meet and join are nothing but the set intersection and set union operation. That can easily be seen. And then we will see that those meet and join operation, that is the set intersection, set union, they are distributive. So this I leave you as an exercise, you can do it. Okay, two more definition I will give and then I'll stop today. So we'll call Z. So in a bounded lattice, it has to be a bounded lattice, otherwise this maximum minimum may not exist, will not exist. So the complement Z of an element X, we'll call Z to be a complement of X if and only if the meet of X and Z is 0 and the join of X and Z is 1. So that's the definition of complementation. Okay, that's the definition of complement. So if you think about arithmetic, I'm doing a very wrong thing. I am kind of explaining you instead of this meet. If you take the if you consider it to be a plus operation and join to be the product operation, I'm doing a very wrong thing again. I'm telling you, you should not be such a non-rigorous in your definition. Everything has to be clearly followed from definition. I'm just giving an analogy. So you see this the usual arithmetic and multiplicative complements. Okay, so okay, but anyway, I should not have mentioned that. Anyway, so Z is a complement of X if and only if X meets Z is 0. So the minimum, if you take the meet of an element with its complement, you get the minimum element. Similarly, if you take the join of an element with its complement, you get the maximum element. Right. So then X and Z will said to be complement of each other. So let us come to this picture. So in the second picture, so what is the complement of C? What is the complement of C? Is there a complement of C? In the second picture, let's say this picture. So let me again state the complement. So X and Z will be complement if the meet of X and J is the minimum element and the join of X and J is the maximum element. So what is the complement of C?
Sir, B and A.
No, it cannot be two complements. There cannot be two complements.
So doesn't exist?
Doesn't exist. Okay, doesn't exist. Oh, no, but that is
Sir,
not
why
possible.
both B and A cannot be? Because both of them satisfy the given relation.
Yes, sir. Both of them satisfy this relation, sir.
Both of them satisfies this relation. Okay, all right.
Yes,
Let us
sir.
say all right, fine. So let us say both A and B are complements of C. Let's say both A and B are complements of C. Okay. All right. So we'll see one. Are you sure?
Sir, but it is not a bounded complete
No, wait.
lattice.
So this is a special property. Wait. Let me make things clear. So let me sort things. All right. So far what we have done, we have defined a bounded lattice. Bounded lattice is one which has a maximum and minimum. We have defined a distributive lattice that we'll come to later. So let's take a bounded lattice. So Z will be called a complement of X if these two holds. Okay. And that's fine. So this is the definition of a complement. Now we'll look at special types of lattice. A special type of bounded lattice. We'll call it a bounded complemented lattice where every element has a complement. So it's not that any bounded lattice is a bounded complemented lattice. Okay. For any bounded lattice, it is possible that some of the elements do not have a complement. But bounded complement lattice is a special bounded lattice where every element has a complement. So let us see which of these is not a bounded complement lattice. Is any of these not a bounded all of these are bounded lattice. Are any of these not a bounded complement lattice? Complement lattice, bounded complement lattice means it is bounded as well as every element has a complement. Every element has a complement. Achha, look at the first case. What is the complement of A in the first case?
B and C, sir.
B and C. Similarly, for B, it is A and C, and C, it is A and B. Okay, so that has a complement. What is the complement of 1?
0.
0. And similarly, what is the complement of 0?
1.
So every element has a complement here. Every element has a complement. So this is a bounded complemented lattice. What about this? The second one, does everybody has a complement?
Yes, sir.
Everybody has a complement. 1 and 0 definitely will have. What is the complement of B? C. What is the complement of A?
C.
And what's the complement of C? Both A and B. Okay, so this is also a bounded complement lattice. What about the third one? Is it a bounded complement lattice? Does every element have a complement? What is the complement of A? Sorry, E. What is the complement of E?
C.
Does not exist.
C.
Why C? Because if it is a complement, then what property we have between A and C? A meet C should be
0.
And A join C should be
1.
So A and C are complement. I think that holds. Does that hold?
Yes, sir.
Yeah, it holds. What about E?
Sir, same C.
For E also is it C? Or E also is
Yes,
it
sir.
C?
So for
What
all
about D?
A, B,
D?
E, D, it will be C.
Yes, sir.
For all A, B, D, it will be C. Okay, so everybody has a complement. So this is also a bounded complemented lattice.
Sir, no, C has 4 complements, sir.
That's fine. We'll come to that later.
Okay, sir.
Okay, now let us prove the next thing. That, or maybe in the next class we'll do it. So this is the definition of bounded. So let us go logically. Logically, what we go? First, we defined what is a complement. Then we gave a new definition of a type of lattice, which is called a bounded complemented lattice. It's a bounded lattice as well as every element has a complement. Okay, so now let us prove this, that if it is a bounded distributive lattice, then the complements are unique, provided they exist. So I am not talking about bounded complemented lattice. So all these are example of bounded complemented lattice. Every element has a complement. Every element has a complement, at least one complement. Okay, so now if you bring in the distributive property, then every element still may or may not have a complement, but if it has a complement, it has to be unique. If it has a complement, it has to be unique. Right, so let me repeat again. So I am talking about two things. First thing is that, okay, the usual definition of complement, every element might have one or more complement. That's not a problem so far. Every element might have one or more complement. Okay, so the first definition, that bounded complemented lattice, what it says is that every element should have at least one complement. It may have more. Every element has at least one complement. So everybody is complemented. Maybe by one or more. I think that holds in all these three cases. That holds. Okay, so now next what we will see, that in addition, if you demand distributivity, still you are not ensuring that it is complemented or not. Every element has a complement or not. But if it has a complement, it will be a unique complement. If it has a complement, it will just have a unique complement if it is distributive. Okay, I think that is easy to prove, but I am not sure we have time today. Anyway, let us stop today. I'll explain this proof, and I'll explain the kind of symmetry you have because of this property. Okay. So this symmetry is very important. See, all these logic structure, Boolean logic structure that we talk about, they have very nice symmetries in the structure, in the lattice structure. And lattice is basically, it came from physics, they call crystal structure, which have a nice symmetry inherent in this. So these symmetries are here, and the advantage of these symmetries is that many of the operations can be simplified because of this symmetry. Many of the expressions can be minimized because of this symmetry. You can minimize many things. We'll see that later. We'll see that moment you bring in this complementation and this distributivity, all these symmetries come up. Okay, I think, thank you. We are overshooting the time.
Sir.
Yeah,
actually yesterday I submitted my file, but it was not proper, so